Hi Bobcats. In this video we'll take a look at how you use the reaction quotient Q. It's really similar to K, but it has a little bit different interpretation. So we will define the reaction quotient Q, and we will predict the direction that a reaction has to proceed to reach equilibrium based on the relative sizes of the reaction quotient and the equilibrium constant. All right, this new thing Q that we are introducing is very, very similar to K, but we use them in different situations. We're going to use K when we know we're at equilibrium, and the word know starts with the letter K, so that's when we use K. We use K when we know we're at equilibrium. Q, however, is what we're going to use when we are questioning whether or not the reaction has reached equilibrium. So if you know it's at equilibrium, we call it K, and if we are questioning whether or not it's at equilibrium, we're going to use Q. So for the reaction quotient Q, the expression for Q has the exact same form as the expression for K. So if we have this reaction where the capital letters represent the chemicals and the lowercase letters represent the coefficients, we can write our expression for Q this way. This is products over reactants. Everybody is raised to the power of their coefficients. But the deal here with Q is that we can use Q at any time. The reaction does not have to be at equilibrium. And once we know the size of Q, we can compare it to K to determine how the reaction will proceed to get to equilibrium. Does it have to go in the forward direction and convert more reactants into products to be at equilibrium? Or does it need to go in the reverse direction and convert some products into reactants to reach our equilibrium conditions? So here's how we're going to interpret Q. This is assuming that you've already calculated a number for Q for your current reaction conditions, and you know the number for K for your reaction. So again, we have our generic reaction quotient expression, Q expression. If we get a number for Q that is equal to K, we would say that the system is at equilibrium. If we calculate a number for Q and it's smaller than K, one way of thinking of that is that if Q is too small, the numerator is too small, that means we don't have enough products. So in order to reach equilibrium, the reaction will have to go in the forward direction, which we say it'll proceed to the right, or it goes in that forward direction. That will convert reactants into products. That'll give us more products. Q will get bigger until it equals K, and we are at equilibrium. But let's say you've calculated Q and it's bigger than K. Well, looking at that Q expression, that means the numerator is too big. We have too many products. So the reaction will proceed to the left. So products get converted into reactants. Q gets smaller as this happens until Q equals K and the reaction is at equilibrium. Let's take a look at this example that involves Q, the reaction quotient. We're given the reaction between COCl2 and carbon monoxide and chlorine, and we have an equilibrium constant value of 2.19 times 10 to the negative 10th. Is the following mixture at equilibrium? If it's not at equilibrium, what direction does it have to go to reach equilibrium? So let's write out our Q expression. Q will be equal to CO times Cl2 divided by COCl2. We have numbers for all of these concentrations. CO is 3.3 times 10 to the negative 6. Chlorine is 6.62 times 10 to the negative 6. And COCl2 is 2.00 times 10 to the negative 3. All right, let's run this through the calculator. We have 3.3 EE negative 6 times 6.62 EE negative 6 divided by 2 EE negative 3. And let me force that into scientific notation, and we get a value of 1.1 times 10 to the negative 8 for Q. What we need to do is compare this to the value that we have for K. K is 2.19 times 10 to the negative 10th. Now remember, when we're comparing numbers with negative powers of 10, 10 to the negative 8 is actually a bigger number than 10 to the minus 10. So we are in the situation where our Q value is bigger than our K value. So we have Q, whoops, I'm running out of room here. I'm going to move up to the top for this. We have that the value for Q is bigger than the value of K. So in that Q expression, that means that we have too many products. So in order to achieve equilibrium, this reaction is going to have to go in the reverse direction, convert some of those products into reactants until Q becomes smaller and equal to K. For this question, I'd like for you to go ahead and pause the video and work this out. You're given the concentrations of all the chemicals, and you're given the number for K. Work out the value for Q, figure out, are you at equilibrium? If not, what's going to happen? So go ahead and pause this. Okay, let's see what we get here for Q. Q is going to be equal to our products over the reactants. So we'll have CO times Cl2 divided by COCl2. Let's see, I'm going to run out of room to put numbers in here, so I'm gonna jump down to the very bottom. For CO, we have a value of 1.1 times 10 to the negative 7. For Cl2, we have a value of 2.25 times 10 to the negative 6. And for the denominator, we are going to have 4.5 times 10 to the negative 2. All right, let's run that through the calculator. 1.1 times 10 to the negative 7 times 2.25 times 10 to the negative 6. We're going to divide that by 4.5 times 10 to the negative 2. That is going to give us a value of 5.5 times 10 to the negative 12. Now remember, that's what we're calculating for Q. K is times 10 to the negative 10th. So Q is smaller than K. One way of interpreting that is that our numerator in our Q expression is too small. That means we don't have enough products present. So to reach equilibrium, reactants will be converted into products until Q gets as big as K. So that means that we have too many reactants, and the reaction will proceed to the right. In this video, we introduced the reaction quotient, Q, and we saw how you can use the size of Q to predict what direction the reaction has to go to reach equilibrium. You can use Q at any time. We don't have to know that it's at equilibrium or not, or that it is at equilibrium. Q is applicable at any time. Now, it doesn't happen often, but every once in a while you'll come across a problem where it's not clear from the initial conditions that we are given what direction the reaction will go. And so that's when we're going to fall back on Q. We're going to use Q to help us figure out, okay, is this going to go in the forward direction or is this going to go in the reverse direction?